Implicit Neural Representation, INR, has gained significant attention due to its ability to characterize signals by preserving the mapping function from coordinates to attributes using neural networks. However, existing INR techniques suffer from spectral bias, where low-frequency components are more easily learned, and capacity-convergence gaps due to inadequate parameters initialization. The proposed Finer++ framework addresses these issues by extending current activation functions to variable periodic ones, allowing for the supported frequency set to be flexibly tuned. This innovation is achieved by modulating the bias vector, or phase, of the variable periodic activation functions, thus enabling frequency tuning. The Finer++ framework is a universal extension of existing periodic and non-periodic activation functions to their variable periodic versions, improving the utilization rate of the definition domain. This framework is demonstrated to enhance the shift invariance and eigenvalues distribution of the neural tangent kernel, NTK, in its Finer++ version, alleviating spectral bias and capacity convergence gaps. The effectiveness of Finer++ is substantiated through extensive experiments on 2D image fitting, 3D signed distance field representation, 5D neural radiance field optimization, and streamable INR transmission, surpassing prior INRs activated with other functions. The proposed initialization scheme for Finer++ is proven to be effective and efficient from both geometric and NTK perspectives. The main contributions of this work include deriving and summarizing three characteristics of existing INRs, building a universal framework to improve INR performance, proposing a novel initialization scheme, and substantiating Finer++'s superiority over prior INRs. This work extends previous explorations by moving beyond the Sine function and achieving superior performance with a wider range of backbone activation functions. Inverse neural rendering, INR, methods have shown promise in representing complex signals and functions. However, they are prone to spectral bias, which affects their ability to capture high-frequency components. To address this issue, researchers have proposed various strategies, including spatial encoding, high-pass filtering, and architectural modifications. Additionally, nonlinearity activation functions, such as sinusoidal, Gaussian, and wavelet functions, have been explored to improve INR's performance. The definition of INR is provided, and its pipeline is outlined, which involves a multi-layer perceptron, MLP, network that characterizes attributes as accurately as possible. The activation functions used in INR are analyzed, and it is noted that current designs focus solely on n-online arities centered around the origin, underutilizing the definition domain. The concept of frequency specified spectral bias is introduced, which refers to the type of frequency determined by the chosen activation function and the supported set of frequencies determined by the empirical scale parameter. This bias is observed in INRs with specifically designed activation functions, which may not be able to represent arbitrary functions. The capacity convergence gap in existing INRs is also discussed, where the function set that INRs can represent can be enlarged by increasing the initialization range of network parameters, but this violates the rule of guaranteeing convergence, resulting in a performance gap between theory and practice. To address these characteristics, the authors propose Finer++, which utilizes variable periodic functions for activating INRs. A unified framework is introduced to extend existing periodic, non-periodic functions to their variable periodic versions, followed by a proposed initialization scheme. The behaviors of Finer++'s supported frequency set and training dynamics under different initialization ranges are analyzed from both geometric and neural tangent kernel perspectives. The authors also present experimental results, which show that the performance of INRs with different initialization strategies can be significantly reduced if the scale parameters are set to 1 and the initialization ranges of network parameters are changed. This highlights the importance of carefully designing initialization strategies for INRs. In the context of image representation using neural networks, the authors propose the Finer++ framework, which introduces variable periodic activation functions to mitigate inherent limitations in traditional activation functions. The proposed framework extends continuous periodic or non-periodic functions to their corresponding variable periodic forms, such as Sine, Gauss, and Wavelet functions. This extension is achieved by composing these functions with a variable periodic function, specifically x equals sin omega f x plus 1 x, where omega f is a parameter to control the overlap between different periods. The authors demonstrate that the central nonlinear components in original functions are repeated multiple times in finer ++. They also show that the frequency increases along the z-axis in the variable periodic versions. Furthermore, they introduce a novel initialization scheme for the bias vector b, which is crucial for tuning the supported frequency set flexibly. The proposed initialization method involves initializing b following a uniform distribution u, k, with a larger range k than the default one in traditional methods. The authors provide a geometrical perspective on the relationship between the supported frequency sets of Sine and finer ++ Sine. They demonstrate that the supported frequency set f omega 0, k of finer ++ increases with the increase of the initialization range of b, and the supported frequency set fp in previous INRs is a subset of f omega 0, k in finer ++. Additionally, they discuss the neural tangent kernel perspective, viewing the training of neural network as kernel regression, and analyzing the diagonal property of the NTK or the distribution of NTK's eigenvalues to understand the convergence of the network on fitting signals. Here is a combined summary of the 2 pages. The paper presents the neural tangent kernels, NTKs, of finer ++, a neural network architecture, and analyzes their properties. The NTKs are visualized in Figure 5, which shows that the diagonal property of the NTKs is enhanced with the increase of the initialization range of the bias vector b. This is because the scale term in the NTK is approximately proportional to the absolute value of the bias, while the sign term differs significantly between diagonal and non-diagonal elements. As a result, the diagonal elements of the NTK increase with the increase of b, leading to a stronger diagonal property. This property provides better shift invariance, allowing the network to learn the signal more effectively. The paper also investigates the effect of different initialization ranges of b on the NTKs and the performance of finer ++. Figure 6 demonstrates that finer ++ outperforms previous INRs in 2D image representation tasks, achieving higher PSNR values and exhibiting robustness to parameter selection. The paper attributes this to the additional parameter k, which represents the initialization range of the bias vector, and enhances the robustness of parameter selection. Furthermore, the paper compares the first layer outputs of finer ++ with those of Sine, another neural network architecture, in Figure 8. The results show that finer ++ captures more high-frequency content in the input signal, leading to a more accurate representation. The paper also discusses the experiments performed to verify the behaviors and performance of finer ++ in various tasks, including 2D image fitting, 3D signed distance field representation, 5D neural radiance fields optimization, and streamable INR transmission. The experimental results demonstrate the effectiveness of finer ++ in these tasks. This research paper presents a novel framework for improving the performance of implicit neural representations, INRs, in various tasks such as image fitting and 3D shape representation. The proposed method, named finer ++, enhances the flexibility of INRs by introducing a new initialization strategy that allows for tuning the supported frequency set in the network. This is achieved by adjusting the initialization range of bias vectors in the network layers. The authors demonstrate the effectiveness of finer ++ through quantitative and qualitative comparisons with state-of-the-art methods on image fitting and 3D shape representation tasks. In image fitting, finer ++ outperforms other methods in terms of PSNR, SSIM, and LPIPS metrics, and provides better visual results with clearer boundaries and fewer artifacts. For 3D shape representation, finer ++ also achieves the best performance in terms of chamfer distance and IOU metrics, and generates more detailed and accurate signed distance fields. The paper also provides insights into the behavior of finer ++ under different initialization ranges and analyzes the role of the first layer in encoding frequencies. The authors visualize the output of neurons from the first layer and show that different neurons in finer ++ focus on different frequencies, resulting in better representational ability compared to previous INRs. Overall, this research contributes to the development of more efficient and flexible INRs that can be applied to a wide range of tasks in computer vision and graphics. The proposed Finer++ framework offers a promising direction for future research in improving the performance and versatility of INRs. The NRF, Neural Radiance Fields, framework is employed to learn a 5D mapping function that maps 3D coordinates and viewing directions to 3D colors and 1D opacity values. This function is used to render novel views of a scene by querying the radiance values along the ray function in 3D space. The Finer++ method is evaluated for this task and compared to 4 classical methods: PEMLP, Siren, Gaussian, and Wire. The experimental setting follows the Wire protocol, using only 25 images for training instead of the commonly used 100 images. The results are presented in Table 3 and Figure 11, demonstrating the advantages of Finer++ for representing high-frequency components. Finer++, Wavelet, achieves the best performance in almost all 8 scenes, and the results of all backbones are improved when Finer++ is applied. The quantitative comparisons in Table 3 show that Finer++, Wavelet, outperforms the other methods in terms of PSNR, SSIM, and LPIPS metrics. The average PSNR values for Finer++, Wavelet, are higher than those of the other methods, with an average improvement of 2.82 decibels. The SSIM values also show a significant improvement, with an average increase of 0.040. The LPIPS values, which measure the perceptual similarity between images, demonstrate a decrease of 0.034 on average. The qualitative comparisons in Figure 11 visually demonstrate the advantage of Finer++ for representing high-frequency components. The reconstructions of Finer++, Wavelet, show more detailed textures and fewer artifacts compared to the other methods. The holes and highlights in the frame of the truck are oversmoothed in the reconstructions of all other methods, while Finer++, Wavelet, preserves these details. The results suggest that Finer++ is effective in representing high-frequency components and outperforms the other methods in terms of quantitative and qualitative metrics. The use of Wavelet as the backbone of Finer++ is shown to be particularly effective in this task. The paper discusses the challenges of streamable INR transmission, which involves transferring INRs between devices with varying resolutions or providing streaming services that require progressively decoding different signal components while ensuring consistency with transferred network parameters. To address these challenges, Cho et al. Propose a progressive training strategy, which involves initially training a small, narrow network to model low-frequency components and then increasing the network width to capture mid-frequency and higher-frequency components. The authors argue that the Siren network used in this strategy exhibits a frequency-specified spectral bias, which limits its expressive power for modeling high-resolution signals under this training configuration. They propose the use of Finer++ in streamable INR transmission, as it is inherently suitable for building streamable INR, especially in cases where the signal has high resolution. The supported frequency set could be significantly manipulated by scaling the initialization range of the bias vector in the widened network parameters. The authors demonstrate the advantages of Finer++ over other INRs in image fitting, 3D shape representation, neural rendering, and streamable INR transmission. They also discuss future work, including designing INRs without any frequency-specified spectral bias. The paper provides a comprehensive overview of the challenges and potential solutions for streamable INR transmission, highlighting the benefits of using Finer++ for this purpose. It also provides insights into the characteristics of existing INRs and how they can be improved upon. The authors present a comprehensive overview of their research team's expertise and contributions to the field of computer science, specifically in the areas of computational photography, optimization for inverse problems, neural rendering, and Gaussian splatting. The team consists of researchers from various institutions, including Nanjing University, Northwestern Polytechnical University, and Vivo. The authors' research interests span multiple domains, including 3D vision, neural rendering, and implicit neural representation. Notably, Zhang, a lead researcher at Vivo, has made significant contributions to Gaussian splatting, AIGC, and neural rendering. His work has been recognized with the CCF Doctoral Dissertation Award nominee in 2021. The team's expertise also extends to numerical methods for partial differential equations and modeling methods driven by data and mechanism. Weibing Deng, a professor at the School of Mathematics, Nanjing University, has worked on analysis and computation of multiscale problems, numerical homogenization methods, and modeling methods driven by data and mechanism. Furthermore, the authors have made significant contributions to the field of computer vision, with publications in top TA conferences such as CVPR and ECCV. Their work has been recognized with several awards, including the 2019 IEEE Broadcast Technology Society Best Paper Award, the 2020 IEEE MMSP Image Compression Grand Challenge Best Performing Solution, and the 2023 IEEE WACV Best Algorithm Paper Award. The author's research has also been influenced by various techniques and algorithms, including neural tangent kernel, physics-informed radial basis network, and marching cubes. They have also utilized various datasets, such as the Stanford 3D Scanning Repository, to validate their research. Overall, the author's research team has demonstrated a strong foundation in computer science, with a focus on computational photography, neural rendering, and Gaussian splatting. Their work has been recognized with several awards and publications in top TA conferences, solidifying their expertise in the field.